Well, good evening, and welcome to another edition of Monday Night Calculus. My name is Steve Kokoska, and I'm joined this evening by my colleague Tom Dick from Oregon State. And in the background is our Texas Instruments expert, Allison Steele. Curtis could not make it tonight, but Allison will be monitoring the chat as usual, and we may be able to ask her a few questions. I'm not sure. Tonight's topic has to do with differential equations and slope fields. This is a really enjoyable topic for me. We always get lots of good questions about this, concerning this topic. And we usually see a question on differential equations on the AP Calculus exam, usually on the free response portion. So I think this is a very important topic for teachers and students. We've actually had some good questions sent to Curtis prior to tonight, and we'll try to get to answer all of those. And Tom will make sure that I don't miss any of those. So once again, Allison will be monitoring the chat. If you have any questions and if you have any answers to our questions, please do correspond with her. And we're going to start tonight with a little technology. Tom's going to look at, I think, the TI-Nspire first. Is that correct?
Yeah, Steve. Well, we'll take a look at both slope fields on the TI-Nspire and on the 84. So,
okay, all yours, Tom.
Okay. All right, I'm going to start out by sharing a TI-Nspire screen.
Okay.
And let's see if that's come up there. I think it's coming up okay. And all right, let's do a little escape there. Okay, so what I've done is open this TI-Nspire document up in a graphs page. And this is probably the graphs environment that most of us would use. Probably 80–90% of the time would be the function environment. But what I'm going to do is go over to the menu, and let's go down to 3 graph entry edit. That's going to have our different kinds of graphs that we can look at. And you can see there we are on number 1 is function. And what I want to do is scroll down all the way to this thing that says, oops, I'm going to hit up arrow. It should wrap back around. There we go. Differential equations. That's the plotter. But people should keep in mind that that is where you're going to find what's called the slope field plot. And that's something that's been in the course description now for a couple of decades, but it was pretty radical when it first came into the course.
Yes, it was, wasn't it?
Yeah. So let me go ahead and hit that. And here we see a lot different kind of entry screen here for entering our differential equation. And it's kind of spaced a little bit funny, but you can see a y1 there, but you see way over here this prime. So this is actually the derivative of y1. And now we can put in an expression that's going to describe the slope of y1 at any point. And so this expression could involve both x and y. I'm going to start out just by putting in an expression with x. So let me try x squared. And I'm going to divide that by 4. Okay, so I've got x squared divided by 4. And down below the expression, you can see there is a space for you to put in an initial condition. That would be a single point that you would like to make sure the solution curve goes through. I'm not going to make use of that right now. I'm just going to make use of this. And so when I hit graph on this, so we enter this, we get what's called a slope field. Now, all a slope field is there's a lattice or sampling of points throughout the plane here in the visible window. And at each of the points here, it's used that expression to evaluate a slope. And then it plots a little segment having that slope. Now, whenever I've introduced slope fields to students for the first time, I often use an example like this, something that they could very easily figure out what the original y1 form would look like. But they're often very surprised when they see this slope field, because when they think of x squared over 4, the image that comes to their mind immediately is a parabola. And so they're expecting a parabola to fit the slope field. But that's not really the case. And we can think about it. Let's see, x squared over 4, that is, its value is always going to be positive. Except at 0, it would be 0. But it will never have a negative value. That means all of the little line segments we see in the slope field should have a positive slope. And we can see when x is close to 0, well, x squared over 4 would be very small. And so we'll have a very small positive slope. As x gets larger in either the positive direction or large magnitude negative direction, x squared over 4 will be a larger number, and now we're seeing a steep positive slope. So this is a slope field that's fitting those slope values that were generated there. Now, I'm going to go ahead and go back to the entry thing and show you a setting that you may want to take advantage of. Notice here it's kind of defaulted back for a second differential equation. I'm going to hit the up arrow to get back to my original here. And what I'm going to do is arrow over, and let's see, I'm hoping that's what I'm trying. Okay, I've gotten into this position. You see this dot, dot, dot to the right there? That's where I want to go. And that dot, dot, dot is just a shorthand, as there's a lot of settings in that dot, dot, dot that we can take advantage of. So I'm going to hit enter, and I get this long scroll down menu. You can see you can choose like Euler's method for plotting your curves, which is a different topic that we're not going to touch on tonight. But let me just scroll down and show you the one setting that I change very often when I'm working with the Nspire. And that's the field resolution. And the field resolution is just controlling how many line segments or how fine of lattice of points is plotted for your slope field. And I find 14 is a little bit coarse. It's a little bit rough. And so what I tend to do is I usually just double that. So instead of 14, I'm going to put in 28. And then I'll say OK. And let's see, let me escape to get the entry line off of there. And now you're seeing a slope field for the exact same differential equation, but it's much finer. And also, I think now you can see, like I said, x squared over 4, what function would have that as a derivative? Well, it's going to be, what, a cubic, actually x cubed over 12, I think, if I did my arithmetic right. But you can see that a cubic would fit the slope field very nicely. In fact, we can try that out by going back to the menu, go back to graph entry edit, and now get the function on there. And without erasing the slope field, we could actually enter a function that we think might fit the slope field. So I'm going to go ahead and see if my calculation in my head was right. I'm going to put in x cubed, and I'm going to divide that by 12. Whoops, I think I might have accidentally entered, didn't I? Okay, so let me get back up. Sorry about that. Okay, let me get back in the entry. I wanted to divide by 12. By the way, when I look at what I did plot, I can tell that's not going to work. Plain old x cubed is clearly not, it's actually crossing a lot of these line segments at an angle that's just not fitting. So let me amend that, put in x cubed over 12. And now I'm seeing a much better fit to my slope field. So that's just kind of the basics of slope field and how you can plot over it. There is also this is a functionality that's resident on the Inspire. You don't have to have CAS or anything. It's on all the Inspires. However, on the TI-84, this is the one spot where if there's one program that you load onto your 84 for calculus, I think this would be the one you'd want to program for, slope field. And I don't know if Steve mentioned this, but slope field questions on the exam are almost always going to be on the non-calculator part of the exam. So when those are assessed, they're going to, for example, expect you maybe to sketch a slope field on your own. But in that setting, it wouldn't make sense for people to have access to something that would just generate the slope field for you.
Right.
Nevertheless, they're a fantastic tool. They're a great thing to have technology generate. But when they're testing whether you understand what a slope field is, they're going to do that on the non-calculated part of the exam. So I'm going to do just a quick stop share and then share back again, Steve, if that's okay.
Yeah, sure.
And switch over to the TI-84. And let's see if I'm able to bring that up. Okay. Okay, here we go. There's the TI-84. And on the TI-84, there's not a resident slope field program, but there is one that you can download for free off of the TIeducation.com site. And we'll make sure people have some information. We'll communicate that to Curtis and Allison so we can make sure people know how to get that. If I go to my programs here, this TI-84 already has one in there. And it's just named SLP FLD, shorthand for slope field. So that's the program. And the way this slope field program works is I'm going to go to y equals, and it's going to expect to see the differential equation for dy dx stored in y1. Now, that means if you wanted to put in something like an expression in terms of x and y, let's do one like that. Say negative x divided by y. That's going to look really peculiar to you because you never see y in the y equals menu as in there. But keep in mind that this is just an expression. And y1, if I have any numerical value for x and y stored, y1 will evaluate using both of those values, okay? So this is where we're storing our differential equation. So dy dx is equal to negative x over y. And if I now quit out of there, I can go to programs, and there's my slope field. I want to execute that program. And let's see, I've got a little bit different window than a standard one, but it's good enough. Okay, so here's whatever window I had. It noticed that it's doing a nice slope field for me, just like on the Inspire, but it was a program that I had to load on there. This might look like ripples of like throwing a stone into a pond and seeing the ripples come out. That's actually not by accident at all. If you think about that negative x over y, that's a derivative you may have encountered when you were doing implicit differentiation. If you do implicit differentiation on a circle equation, like an x squared plus y squared equals 9 or something like that, the implicit derivative turns out to be negative x over y. And so we can see the solution curves in this case are going to be parts of circles. So that's kind of cool. And again, if you did want to plot a function on top of this, you could just use y2 or y3 or any of the other equations, y equals things. Notice the slope field's already on there. It's not selected. But I'll go ahead and y2, I'm going to put in the square root of, I mentioned x squared plus y squared equals 9. Well, let me solve that for y. So that y would be the square root of the quantity 9 minus x squared. And let me graph that. And boom, there it is. There's a nice curve, and it's following the fit of the slope field. So again, slope fields on the exam, it's probably going to be on the non-calculator part of the exam, but for practice and for especially for seeing whether the solution to a differential equation is plausible, what I mean makes sense, is you could do a slope field for it and then take your solution and plot it on top of the slope field and see if it fits. If you see any discrepancies, that's a surefire tip that something's gone awry in your calculation somewhere that you need to take a look at. All right. I think I've wagged my tongue enough, Steve, so I'm going to turn it over to you, and so you can dive into your questions. So
Tom,
I'll
before
stop
you
this.
leave that,
And while
before you
we're
leave it, go ahead,
go
Ellen.
ahead.
while we're doing that, I did just want to give a shout out. We've got quite a few joining us from Miss Connolly's class, as well as the famous Mr. Crowley's class this evening.
All right, great. Shout out to Mark.
Hey, Tom,
Okay.
before you leave the screen,
Yes, sir.
one quick question. So what do you do in order to sort of erase the slope field? Is there some special command for that? So now I'm all done with this and I want to graph another function. I'm going on to another problem. How do I sort of erase this and start over?
Sure. Yeah, no, good point. Actually, any change at all you would make to the window would get rid of the slope field. So for example, if I was to just do a zoom decimal here,
Yes. I see. Okay.
I've got a fresh screen. It went ahead and still graphed that function I had entered into Y2.
Okay.
But the slope field, for me to generate a new slope field in a new window, I also need to rerun the program.
Gotcha.
So if I say, oh, the slope field, I really want to look at it at a different part or a different window, I'd go change my window, but then I would need to go to quit to the kind of the home calculation screen, pull up the program, just run it again.
Gotcha. Okay.
Yeah, no, that's an excellent question. Is if you're wanting to wipe the slate clean, just change the window, and then you could even go back to the old window you had, but now you won't have the slope field there anymore.
Okay.
So, all right.
Okay. Very good.
All right. I'll stop the share. It's all yours, Steve.
All right. Well, let's take a look, if we can here, at some of the problems and solutions that we posted on differential equations and slope fields. So I'm going to try to write a little bit here. And this first problem involves trying to connect the differential equation with the corresponding slope field. And I think, Tom, correct me if I'm wrong, but this is the kind of a problem that a student might see in the multiple choice portion of the exam.
Oh, yeah, absolutely.
Right?
Yeah.
Might get a differential equation and say, okay, which of these four slope fields corresponds to this DE? Okay. So when I solve these problems, I mean, I'm always looking for some sort of prescriptive way to do this, kind of a step-by-step process. And I don't know if there is one, but here are a couple of things that I do in trying to figure this out. I might look at what happens when I hold, say, y constant. And I might look along, for example, a horizontal line, and I might ask, well, does the slope change? Do those slopes of the line segments change as x varies? Well, if they don't, well, that would suggest that x is not involved in the differential equation. And similarly, I might look along a line where x is constant and see, well, are those changing as y varies? If they're not, then that suggests to me that y might not be involved. Now, another thing that I frequently do is I take a look at the first quadrant where both x and y are positive. That somehow seems to be easiest, the most intuitive for all of us. And it's almost easy to plug in a couple of values and see what's going on. So I always look in the first quadrant. And finally, the last thing that I do is I kind of look for any special circumstances in the differential equation. For example, are there any places where I know that the derivative is going to be zero? And can I identify that pattern in the slope field? So I'm actually going to start there by looking at A. if I look at that differential equation, one of the first things I thought about is, when will that derivative be zero? Well, let's see. If I can scribble a little bit up here, Tom, let me know if you can see this. If I scribble a little bit up here, if y were equal to x over 2, then that derivative would be zero. And y equal x over 2 is a straight line through the origin. So if I can find any one of these slope fields where, in fact, I have zero slope along that line, y equal x over 2, I'm feeling pretty good about this. And in fact, if I look real closely over here, I'm going to scribble a little, Tom. I think there is a line in there. There it is. Y equal x over 2, where in fact the slope is zero. Now, I can also argue, now that I've got that, I can also argue, think about what's going on above that line. Is y bigger than x over 2? Is it less than x over 2? And how does that affect the slope? And take a look at those line segments. But boy, that's a very good start on that one. So A corresponds to slope field 2. We're going to look at B. Here's what I saw over here in B. I saw a product. And I thought, well, how do I make that product zero? The only way to do that is if one of the factors is zero. So that means if x is zero or y is equal to minus 2, the derivative is going to be zero. So I'm looking down here at slope field 3. Right here, where y is equal to 2, I have those line segments with slope 0, as expected in that differential equation. And right here, sorry about this kind of funny arrow, but right there along the y-axis where x is equal to 0, if you can see those little green line segments, they have slope 0 also. That's pretty cool. Now, I think another thing you can see here is probably in the first quadrant pretty easily, where both x and y are positive. In fact, where x is positive and y is greater than minus 2, the product there is going to be positive and the slope going to be positive, and that's over in this area here. And I'm feeling pretty good about this. I think B is connected with slope field 3. Cool. C, how about this one? Well, here's what I saw over here in this one. Once again, I was thinking about, well, when is that derivative going to be zero? Well, I can kind of see that equation on the right-hand side, and I'm thinking, that's kind of related to a circle. I'm going to scribble a little bit off to the side here. X squared plus y squared equals 4. Well, I know that if I pick an x and a y that satisfy that equation, it's on that circle, and that's going to make that derivative zero. And so it seems to me that on this circle, x squared plus y squared equals 4, man, those line segments better have slope 0. Now, I didn't take a very fine resolution as Tom was talking about, but I think you can kind of see along the circle, the line segments have slope 0. What happens outside that circle? Well, outside that circle, x squared plus y squared is going to be greater than 4, and therefore the derivative is positive. And so look at all those line segments outside that circle. They all have positive slope. I'm feeling good about this one. And inside the circle, that expression x squared plus y squared is less than 4. And so I better have some line segments that are negative, and in fact they are, which is pretty cool. So C goes with 4. Finally. This is kind of
do this one, Steve. I think I can do this one.
What's that?
I think I can do this one.
You can match this one. Well, this is kind of a cool one. Maybe I should have done this one first. Y prime is the cosine of e to the minus xy. I'm not sure exactly how to start on this one, except maybe looking in the first quadrant. I mean, what happens when both x and y are positive, and what happens when both x and y increase, get large? Well, let's see. When both x and y are large, that product is large, and this is very large negative. What does that mean for e to that value? Well, that makes e to that expression, e to that value small, close to 0. And what's the cosine of 0, a value close to 0. Son of a gun. That's going to give me a 1. And so it seems as x and y get large, increase without bound, that argument of the cosine is getting very close to 0, and so the derivative should be getting close to 1. And in fact, that's what's happening over here. And that's exactly what happens over here, because in the third quadrant, x and y have the same sign, so their product is positive, and then there's that extra negative there in the exponent, which once again drives that argument close to 0, and we get a slope of 1. That's really cool. Over here in the second and the fourth quadrant, I think if you consider, say, look along horizontal lines and let x vary, let x increase, I think you can argue that there's going to be some sort of cycle here. We know that the cosine cycles, and there's going to be some sort of cycle here as x increases. It's not quite evident in the second and the fourth quadrant in my drawing. Again, my resolution isn't that great, but I'm pretty sure D goes with 1. Cool.
Say, Steve,
Yes, sir.
like on your part A there, on the exam, will they include that Roman numeral 2 right after it?
I don't think so, Tom.
Okay.
We could lobby for that. Good question. All right. I have a couple of problems here in 2 where we're just going to solve the differential equation. These are not initial value problems. We're simply going to solve the differential equation. A couple of the questions that were sent to Curtis dealt with including this constant. So I'm going to try to make sure that I'm very careful as I speak about these constants and when they arrive, when they should be put into this equation, when they should appear. All right, so the only kind of differential equation that students need to know how to solve are separable. And what does that mean? Well, I can separate the variables. I can bluntly put all the y's on one side and all the x's on the other. So, okay, here's my differential equation. I'm going to get all my y's on the left and all my x's on the right-hand side. Here we go in this step. I'm going to integrate both sides. On the left-hand side, I get a log of the absolute value of y. A question we often hear, Tom and I often hear is, well, do you really need to worry about including that absolute value symbol? And the answer is yes, especially when we're dealing with initial value problems. Yes, you need to include it. We'll get rid of that, or we'll take care of eliminating those absolute values as we eventually solve this for y, but yes, you definitely need it at this step. On the right-hand side, and this is an integration almost by inspection, but it's really substitution with u equal to minus 2x. I'll make maybe one more step here. So du is minus 2 dx. So that's an integration by substitution. I think that gives me a minus 1/2 e to the minus 2x. And this is the step right here where this constant c has to come in. So where I find an antiderivative of the left side, I find one of the right side. I've got to add that constant plus c. Not a silly question, but sometimes we get this one. Well, really, when I find the antiderivative on the left and one on the right, there's really two constants. Agreed? But I've combined all of those and brought it over to the right-hand side. So now what do I do to isolate y? What do I do to get an explicit expression for y? Well, I'm going to exponentiate both sides. On the left-hand side, e and log are inverse functions, so I'm left with the absolute value of y. On the right-hand side, kind of hard to see, but that expression, minus 1/2 e to the minus 2x plus c is all in the exponent. I'm going to use some properties here of exponents so that I've got an e to the c times this expression. And e to the c, I will just abbreviate or use some other notation and call that a different constant, c1. Now, how do I isolate y? Well, I think about this as that argument can be either positive or negative. And if it's positive, in my mind, I'm on one branch of this solution or one piece of the solution. If it's negative, I'm on another piece of the solution. So it's either going to be a plus or minus y when I evaluate that absolute value. And we will incorporate that sign into this constant C1 and write that as a different constant C2. Now, I didn't ask for this, but I actually created or included in the solution files here the slope field associated with this differential equation. And teachers, students, you might think about this. Does this make sense with the differential equation up above? Can you justify, can you reason out that this equation for y, can you draw that on this slope field? It might not be fine enough for some of this, but does it make sense that that equation somehow fits in this slope field? So we'll leave that as kind of an open question. Here's B. Let's try this one. This was kind of a cool one too. I like this one. So dy dx is e to the x minus 2 over the cosine of y. I've got to separate the variables. I'm going to bring all the y's to the left once again, all the x's to the right. I'm going to integrate both sides. Here we go. The integral of the cosine of y. Well, that's an integration by inspection, one of our common anti-differentiation rules. That's just the sine of y. On the right-hand side, integrate term by term. So that's just e to the x minus 2x. And here's where my constant c comes in. And this isn't so bad. I mean, I want to solve for y. In order to do that, I'd have to take the inverse sine of both sides. So here's some things to think about, and then I'm going to hand it over to Tom here. I was thinking about this. I drew the slope field for this, and I was thinking about this, and, well, wait a minute. What's the domain of this function? Do I need to worry about that, or do I need to think about that? Here's a question for the chat, Allison. What's got to be true about this argument right there? What has to be true about that argument in order for me to be able to evaluate the inverse sine or the arc sine? And the reason that I thought a little bit about this was because I didn't think originally that this slope field actually made sense. So I started out by thinking about the domain, and I'm going to turn it over to Tom to see if he can justify a little bit of this with technology. Okay?
All right, let's give it a shot. Okay, I'll go ahead and use the 84 on this one, I think.
Okay, sounds good.
And so I'm going to go to my y equals menu and clear out y1. And remember, on this slope field program on the 84, that's y1 is where we'll store our differential equation. Let's see, this was actually a fraction. So I'm going to do this alpha of the xt theta key, get a nice little fraction there. Okay. And let's see, I think it was e to the x.
Yep.
Minus 2.
Correct.
That's my numerator. And then down in the in the denominator, we've got the cosine of y. Again, it's a very weird looking expression to have in y1, but that's just our placeholder for the differential equation expression. And let me go ahead and clear y2. And now I'm going to go back to the calculator screen and bring up the slope field program. Now, since we had run the slope field program before, I can either pull it out of programs, but since they're before, if I just hit enter, it's going to run it again with this new differential equation in there. And hopefully we'll get a slope field that looks not dissimilar to the one that Steve had. Okay, it might look a little bit different just because of the way the lattice is laid out and stuff, but this is looking
pretty good, Tom.
Looks
pretty good. Yeah.
And now we're going to check out and see if Steve's solution makes sense. I'm going to go back to the y equals and go to y2, we didn't have an initial condition. So to get a particular solution, I'm going to need to pick a value for c. So what we could do, let's see, I think the general function was the inverse sine of e to the x minus 2x.
Mm-hmm.
And then inside the parentheses, that's where that plus c showed up. So we could put in a value here. We've got to be a little bit careful about the plus c because, as Steve said, the domain of the inverse sine, that's going to be limited to between -1 and 1.
Right.
So whatever I have in here, it's got to be something that I'll get some values between -1 and 1. So I'm going to put it, let's see, e to the 0 is already 1. But I am subtracting x. So you know what? I'm going to put in maybe 1/2. Cross my fingers. So that's one value of the c that we could try out. And let's graph it. And I don't think I picked a very good value.
No, I don't see it, Tom.
I don't see it. It might be off the screen.
Yeah.
So I'll tell you what. Let's go back to y equals. I'm going to make the plus c, the c value just 0, I think. See
Yeah, let's try that.
Okay. That's a perfectly good value of c. Now,
Yep.
whether that's going to be one that we'll see some curve for. We'll see. Oh, you know what? We lost our slope field because I did a new graph there. So let me just run the slope field again.
Okay.
Regenerate it. Doesn't take too long. And now I'll go to y equals, turn on y2 again. And now we'll graph it. And this time it should graph on top of the slope field. Oh, there we go.
How about that? Yeah.
Great. And it looks like a pretty good fit, though. It's, you know, it's in a pretty, there's not that many line segments there. So something we could do is we could change our window to maybe just being the first quadrant. So I'm going to make the x min 0, the y min 0. Now, when I do that, what I'm going to need to do is run the slope field again to generate a new slope field for the first quadrant.
Mm-hmm.
There you go.
So when that runs, Tom, does that turn off all the other y's and y?
It does. It automatically turns off all the y's. And then it's just referring to y, even not y1 itself isn't even selected. It uses y1 inside the program just to evaluate what the slope should be.
Gotcha.
And then pops these little line segments.
Okay.
And when I go back to y, notice that y2 was turned off.
Yep.
Need to turn it back on and graph again. And I get a little bit more. So you can see I changed the window a lot. Each time I change the window, I do need to run the slope field program again. But this is looking like a pretty good fit.
Pretty cool.
All right. So did you want to look at anything else on this, Steve, or should I just
let's see. We had a suggestion.
Okay.
Try a C of -0.5.
Okay. Be
I
happy.
don't know if that'll work. Try that one and see if that
And
does
you know
it.
what? I'm going to make that my Y3.
Okay.
So let's make I'll just go ahead and enter it again, since that plus C was inside the parentheses. So minus 2x. And the suggestion was minus 0.5?
Yes.
Okay. And let's graph that.
Hey, how about that?
Nice. And notice it has a bit wider domain to it.
Yes.
Very cool. Great. And
How
so
about that?
you can see that you can actually do multiple solutions for different values of the constant on this same backdrop of the slope field.
Yep.
Very nice. Okay. Stop the share there and back to you, Steve.
All right. Deal. Here we go. So there was one question that came in here about that constant C and that one problem we did, Tom, I guess it was A, where it changed from a C to a C1 to a C2. And the question is, do students have to do that on the exam? And the answer is probably not. We are very forgiving about that C. As it changes, quote unquote, you can just keep the same symbol C. You don't necessarily have to have a subscript. I don't think students would lose a point for that, in my opinion.
Yeah. And it was kind of it is kind of a subtle thing. I mean, your C1, Steve, I don't know if you want to back up to that page.
Yes.
I mean, your C1 is really an arbitrary positive or non-negative constant.
Yeah.
So you got an absolute value of y is
Right.
an arbitrary positive constant times this e to the negative 1/2. Well, that means y itself is either plus or minus that arbitrary positive constant. Well, you could just say that's just an arbitrary constant, period, which is that's your C2. So the C1 was arbitrary positive, but C2 is just plain arbitrary. It took care of both positive and negative, and that's why you were able to drop that absolute value sign.
Yep.
I think the way on the exam it kind of gets around that is you often have some initial condition you have to work
Correct.
with, and that's the thing that resolves the matter, and then it's cut and dried whether you're using the positive or negative branch of your
Correct.
absolute value.
Correct.
All right.
Okay, I hope we do have the opportunity to look at one of those here. Let's see. Let me take a look at C. We'll solve one more or maybe two more quick differential equations, and then we'll take a look at an initial value problem if we can. Once again, I'm going to get all the y's on one side of the equation, all the x's on the right-hand side. I'm going to integrate both sides. This one's pretty easy. This is one of our anti-differentiation rules, common anti-differentiation rules. That's an arctangent. On the right-hand side, this is again is a substitution with u equal to x squared plus 1 and du equal to 2x dx. So let's see, I integrate on the left-hand side, I have the tangent inverse. On the right-hand side, I had this expression in x. There's my plus c. And again, not too bad to solve for y. What's the inverse of the inverse tangent? Well, the tangent, I have to take the tangent of both sides. And here's my expression. Can I take the tangent of any argument? Yeah, I guess I can. So I don't have to worry too much about that domain. Does that function y fit nicely into this slope field? Well, again, we'll kind of leave that for teachers and students to think about. I provided that slope field here. You might try to draw this function by looking at that slope field. Good.
So, Steve, that tangent function, it will have just some isolated places where it's not defined, right? Because
you're correct.
But there will be some whole stretch of numbers where it's undefined. I think that's what you think about.
Yep. All right, well, let's take a look at 3 here. We're going to solve some initial value problems. I like this one. This produced kind of a weird slope field, although this did not ask to do that. I had to see what was going on here. So here's the differential equation. dy dx is x plus 1 divided by the square root of xy. We have this condition y of 1 is equal to 4. I'm going to start out in the usual way. Here's all my y's on that side. Here's the x's on the right-hand side. And looking ahead just a little bit, how am I going to be able to integrate that? Well, the technique is to write that as 2 separate terms or 2 separate fractions, and to write each of those terms as x raised to some power. So I did that over here. Now I'm going to integrate both sides. Don't let me make a mistake on this one, Tom. On the left-hand side, 2/3 y to the 3/2. On the right-hand side, we integrate term by term, and here's the plus c. It is at this step now, right at this next step, is where we recommend that students use the initial condition. Look, can you go on and solve this for y? And then once you have isolated y, use the initial condition at that point? Absolutely. But in my opinion, not only is that harder, but I think it introduces more chance of an error. So the best thing to do is, once you have found the antiderivative of both sides, included your plus c, use the initial condition right away. So here's the y equal 4. Here's the x equal 1. And saving a little bit of time here, I think that gives me a c equal to 8/3. So I went back up here, plugged in a c equal to 8/3, and I multiplied both sides of that by 3/2. Here's an expression almost with y isolated. How do I do that? Well, how do I get y all alone? Well, I raised both sides of this equation to the 2/3 power. And here's kind of a weird looking expression for y. Now here's what I did down at the bottom, and I may need a little help with this, Tom. So when I drew this slope field, I was kind of, I didn't know what was going on initially here, but I only got a slope field in quadrant 1 and 3. I wasn't quite sure why. So we'll leave that as a question for participants. Why isn't there any slope field for this differential equation in quadrants 2 and 4? Well, the second thing I did was I wanted to actually draw this particular solution curve that goes through the point 1, 4. So here it is. Here's the point 1, 4, and it looks like this. So my next question is, where x is equal to 0, is that actually on the solution curve, or should there be an open circle there, I wonder? So that's something else you can think about. Allison, we'll let you monitor the chat and let us know if we get any answers to those questions, okay? Or those are good ones maybe for 8 o'clock tomorrow morning in class. I liked that one, Tom. Take a look at B. Oh, this has some good things in it too. So here we have dy dx is equal to y minus 2 over 1 plus x squared. We have another initial value problem. Y of 1 is 3. This is a separable differential equation. I can get all the y's on one side, all the x's on the other. And this one involves the log of an absolute value. And let me make sure that I do this correctly. So on the left-hand side, this is the log of the absolute value of y minus 2. Do you need the absolute value? Yes, you do. You have to worry about that. On the right-hand side, this is a common anti-differentiation formula. This is the arctangent, tangent inverse of x. And here's my plus c. Okay. At this step, at this point, we want to use the initial condition. What was it? Y of 1 is equal to 3. So y is equal to 3. There's the x equal to 1. And that gives me a c equal to minus pi over 4. But it's also told me something else here. This is the way that I think about this. When I plug in that y equal to 3, this argument here, this argument inside the absolute value is positive. And that tells me I am on the branch of this solution where that argument is positive. If you think about, for example, the graph of the log of the absolute value of x, just think about that. I'm going to scribble a little bit. If you think about that graph, it's not defined. That function is not defined at x equals 0. And there are two pieces, two branches to that. One branch corresponds to where x is positive. One corresponds to where x is negative. In my mind, that's kind of what's going on. And I need the branch in this case where the argument is positive. That means in my next step, I can simply drop the absolute values. How do you take the absolute value of a positive argument? It is just that argument. I don't need that extra negative sign. So, okay, I've got the log of y minus 2 is equal to this expression with an arctangent over there. I'm going to solve this for y by first exponentiating and then adding a 2 to both sides. There's my expression for y. And there's some cool things going on here, I think, in this slope field and this equation. There's the slope field. It kind of looks like that the line segments have slope 0 at x equal 2. wonder if I could justify that. I think I could if I look back up at the differential equation. And I drew in this curve that satisfies the initial condition of 1, 3. Now, don't be misled here. If you look at this very quickly, it seems like there might be some horizontal asymptotes on the graph of y. And it seems like there are two horizontal asymptotes might be at y equal 2 and y equal 4. But they're not. And so a question is, can you find the horizontal asymptotes on this graph of y? I wonder if the slope field might be just a little bit misleading in finding those. Okay, we'll leave that as an open question. I like that one. Have we got time for one more? I think so. Maybe a couple more. All right, and C, holy Toledo. This is complicated on the right-hand side. I'm going to bring all the y's to the left, all the x's to the right-hand side. Oh, it's not so bad, I guess. The integral of e to the x is just e to the x, and this isn't bad on the left-hand side either. That's a simple substitution with y equal to 1 plus y squared, I believe. The derivative of u is 2y dy. The 2y is part of the integrand product, except for that constant 2, so we should be able to do this. I integrate both sides. There's my constant c. I use the initial condition. It turns out that c is equal to 1. So I'm going to go back up here and I'm going to plug in a c equal 1. There's my expression in x and y. Can I solve that? Can I isolate y? And by the way, sometimes you cannot. Here I think I can. I'm going to square both sides. I'm going to subtract 1 from both sides. And then I'm going to take the square root of both sides. Whoops, there's my expression for y. And I did the same sort of thing down here. I drew a slope field and I drew in the solution curve that goes through that point. What was it? What was that initial condition again? I think it was 0, the square root of 3. So there's another question I have here. You know, as I look at that solution curve, it looks an awful lot like y equal e to the x. Yes, granted, it does not go through the point 0, 1, but it still looks an awful lot like y equal e to the x. And I wonder if you can make an argument to explain that, to justify that. Why does that solution curve look a lot like y equal e to the x? Boy, lots of open questions here. You're going to have to be writing lots to Curtis this week, I think. All right, I'm going to take a look at 4, Tom, and maybe we'll call it a night. This is a good one here.
Say, Steve, just wanted to throw out that, you know, that problem you had a couple back where when you did the slope field, it only showed up in the first quadrant.
Yes,
and the third quadrant.
Yes.
I believe in the chat, Wanda Burns pointed out that square root of the product of x and y might be the culprit there. And
indeed it is. Yep. Very good one. Yep. There's a square root of x times y. And in the second and the fourth quadrant, that product would be negative. And of course, the square root would be undefined. And that's exactly why we don't have any part of the slope field in there. Very cool. Very cool. All right, this was a nice one, and I actually discovered something, Tom, on Mathematica when I was doing this one and produced an extra graph here just for the heck of it. The first thing I asked is to use technology to sketch a slope field for the differential equation. So I don't know, maybe we could end if you want to take a look at this one eventually, but this is what I got using Mathematica. And I used this slope field to sketch the solution curve that goes through the point 2, 1. So there's the point on the graph 2, 1. And I did my very best to sort of sketch following those line segments to draw a rough sketch of the solution curve. Something sort of very interesting seems to be happening here. I hope that I can explain this before I end this problem. But it looks like as we go over here in the third quadrant, it looks like that curve is following the line y equal x. It seems awfully strange to me, but it seems to be doing that. I was looking something up in Mathematica to try to make my slopes fields, give them a couple of more options, make them look a little nicer. And I happened across a an option that allows you to draw, well, what I would say are several solution curves in here. And I don't know if you can see this, Tom, but you might be able to see the green sort of arrows in there. Those correspond to my solution curve that I drew up above. That's the curve that goes through the point 2, 1. That was kind of cool. Gives me even a better picture of what's going on. And those arrows actually, those vectors actually represent those little line segments. Very cool.
Yeah, I believe somebody in the chat was asking about using slope fields to do vectors, and I think those are called direction fields, and similar idea there.
Yeah, very cool. Yeah, I think when I did that, when I produced that, if I let me go back to that for 1 second. I think when I produced that, one of the options that I gave Mathematica was something that would produce those vectors so that they all have the same length. But there is another option that allows you to adjust the length or the magnitude of that vector. So that can be useful in other applications. All right, so we're still working on the same problem. Let's see if we can solve this differential equation. I'm going to bring all the y's to the left, all the x's to the right-hand side. Well, this doesn't look too bad. I've separated the variables. Simple substitution on both sides. U is equal to minus x, u is equal to minus y. I get this expression. We bring in the plus c. We use the initial condition. And I found this value of c. Now, that was a little cumbersome for me to write. So what I did is I just said, well, that's my value of c, and I'm going to assume that and solve for y here so that I didn't have to write it out all the time. I did that. I exponentiated both sides. Pardon me, I took the log of both sides. And I think I am left with this expression. I multiplied through by a -1, by the way, in order to make that a little bit easier to work with. And there's my expression for y. And what I did here is I actually used that explicit value of c. And I thought a little bit about the domain here, and I think the domain here might be all reals, okay? So I'm going to add this graph to my slope field, and son of a gun, it looks an awful lot like what I drew on the previous page. And I wonder if we can justify this part over here. What's going on over there? Can we justify that at all? I wonder. So as x increases negatively, what's happening inside here? Well, as x gets bigger and bigger, let's see. This is going to be a small number, so that's inconsequential. As x gets bigger and bigger, let's see. If that's inconsequential, then this is just like the log of e to the minus x, and those are inverse functions, right? So that's just going to give me a minus x. So it's like I've got a minus x, which is just x. And remember, x is negative. And so this is really just the line y equal x over here in the third quadrant. That's really cool. So I saw that on the slope field. I wasn't sure that it really made sense, but I think we can actually justify that. Pretty cool. Tom?
Well, Steve, I was looking at your original differential equation, so up the page there a bit.
Yes.
On the line y equal x, my derivative will be exactly 1.
How about that?
Because my e to the negative x and e to the y will cancel out and give me 1. But y equals x is a line of slope 1. So it's all kind of falls into place. So kind of cool.
How about that?
I think we're just about out of time, Steve.
Okay. We're going to post these problems with Allison and Curtis tomorrow. We do have one overtime problem. I've seen several of these in the Facebook group recently, Tom, and this is a very common sort of free response question. So I've got this one here in the OT portion of our presentation, and we'll post this question and answer tomorrow.
Great.
So great. Thank you very much for joining us.
A final wrap up before we close up. I just wanted to share the last of the chat was noting that the vector direction fields are very informative for golf. And in fact, there was some conversation about seeing that type of, it's fun to see part of math teacher's job showing up on TV.
How about that? Thanks, Allison. Great job. Thanks, Tom.
Thank you, Steve.
Okay, very good.